Okay, good evening, everybody, and welcome to another session of organic chemistry. Okay, of course, in today's session, we are going to start with chapter 2. But before we do that, and also before we also do the problem set that you guys have just taken in the short quiz that I just gave you, before we do both of those, let me make a couple of announcements. Every Wednesday, so you may want to mark your calendar, every Wednesday we are going to have review session, online review session, and you should use the link that I sent you yesterday for all of the sessions. Okay, that's every Wednesday at 8 p.m. unless I tell you otherwise. Also, the quiz that you took on Tuesday, I do have the quiz available to give back to you. So make sure you stop me about 5 minutes to the end of class today, so I get a chance to give them back to you. I'll call your names. That way I get to know you guys. Yes. Which one? Which test on Wednesday? Is it graded? No, it is part of your class participation. Okay. So anyway, we are going to start with chapter 2. But before we do that, let us go over the quiz that you guys have just taken. Dwayne, can you go ahead and read this course? Continue. Okay, very good. So what we want to do here, this is question number 1. You have a formula C3H6 and 2 chlorine atoms. And of course, the first question here is, how many valence electrons does this molecule have? How many valence electrons? Anybody? How many? 32? Okay, how did you, that is correct by the way. How did you come up with 32? That is correct? Yes. Okay, in other words, you added together all of the valence electrons for the individual atoms that are present in that molecule. Okay, very good. So that is essentially what we need to do. Okay, so we don't need to do any more than that. So the answer is 32 valence electrons. Of course, you know that the valence electron for carbon is 4. You have 3 of them, so that is 12. Valence electrons for hydrogen is 1. You have 6, so that is 6. And the valence electrons for chlorine atom is 7. Since you have 2 of those, that is 14. That is how you end up with 32. So that's 14, 6, plus 12. Okay, very good. How about the next one? Write the Lewis structure. Okay, Kala, do you want to help us with that? You didn't know I remember your name, did you? Okay. Okay, anybody want to help us with that? Yes. Yes, Dwayne?
3 carbons in a row.
3 carbons in a row. Okay, very good. Oh, I'm sorry. 3 carbons in a row. Keep in mind we want to write the Lewis structure, right? Okay, so then what do you do? Okay, for the Lewis structure, how do you represent the bonding electrons? 2 dots. Okay, very good. Keep in mind, at this point you have 32 valence electrons, right? Okay, so you have the...
Oh, what if we don't put the dot?
You have to. That is Lewis. For Lewis structure, you represent each covalent bond by 2 dots. Okay, so we have, you want to place hydrogen here, right? Another hydrogen here. Another hydrogen here. Hydrogen here. Okay. Two chlorines. Okay. Okay, everybody agree with that?
No. That needs to be another A.
How many hydrogens do we have here? We have 6. Wait. Okay, let us see here. So you say you have hydrogen. Okay, we have 6 hydrogens already. So what's wrong with that? What is wrong with this here? Huh? It's not what? Okay, very good. We got to add the rest of the electrons on where? On the chlorine, exactly. Keep in mind with the Lewis structure, you got to show all of the bonding electrons by using dots, and then you show all of the non-bonding pairs of electrons also. So here you also have this here, and this here. Okay, do we agree on that? Okay, so can we move on? Okay, very good. Yes. That's fine. That's fine. And the chlorine could be anywhere. I did not tell you which structure to draw. I say any structure. Okay. Okay, very good. So now the next one is write this skeletal structure of the molecule in part D above. In other words, I want you to use this part D, this here, whatever answer you have here, to be what you use for the skeletal structure here. Oh, okay, so what would that look like? Huh? Yes. Okay, you just do. Okay, we do this. Okay. Okay. Huh? There are 3 carbons there. This is a carbon. This is a carbon. Well, let's start with that. Let's have some quiet. This is a carbon here. Let's call this carbon number 1, number 2, carbon number 3, right here. Okay? Okay, do we agree on that? Okay, very good. Yes.
Are you going to have credit for me if you put 1?
Okay. Okay, so anyway, so that is question number 1. So this is a very simple question. 6 points each. 6. The quiz is a total of 12 points. Okay, let's go to our question number 2. Yes. Which one? Do you have to place the chlorine on carbon 3? Oh no, you don't have to. Yes. In other words, yeah. Yes. Okay. For example, I think this is the question you are asking me. Supposing we have this. Wait. Supposing you have this, right? And then here, you could do that. That would be an acceptable Lewis structure, okay, for that molecule. Okay, the only problem now is whenever you want to draw the skeletal structure, you got to draw the skeletal structure of this here. And what would that look like? What will it look like? What will it look like? Exactly. Okay, so that would then become okay. Okay, so let's go to question number 2. Okay, somebody read question number 2 for us. Yes.
The aniline molecule below indicates the hybridization with all carbon, nitrogen, and oxygen atoms.
Okay, very good. Okay, how many of you have heard of adrenaline before? You heard of adrenaline rush? Exactly. That is the that is the molecule that the body makes when when you are in trouble. It gives you a rush to get out of the trouble, or just it increases your heart rate. So whatever you want to do, you do it very, very fast. Anyway. So this is a very important biological molecule. Hopefully by the end of this semester, all of you guys should be able to synthesize this type of molecules. Okay. So now we want to do the hybridization. Let's start with the carbon atoms. What is the hybridization of this carbon here? sp2. Here. Here. Here, this carbon, sp2, this carbon, this, about this one here, sp3, okay, about this one here, what is it, 3? Okay. Is that okay with everybody? What is not okay? Okay. Let's have some quiet, yes.
When you get towards the end where it breaks out, that's what we see, like, by the nitrogen, it's an sp3.
Mm-hmm.
How are you telling that?
Because this carbon is bonded to 4 other atoms. It's bonded to 3 hydrogen and a nitrogen. Okay, about this carbon here. sp3, very good. Okay, now let us take a look at the oxygen. About the oxygen atom, this oxygen atom here. What is the hybridization of oxygen atom? How do you know that? Yes. Okay. Excellent, very good. So here, this oxygen has 2 pairs of non-bonding electrons, and each pair of non-bonding electrons should be considered as a bond. And as such, this oxygen, you think of it as being bonded to 4 different atoms. So therefore, this is sp3 oxygen. Okay, about this oxygen, the same thing too. That's sp3 also, oxygen. About this here, okay, the same thing, sp3. About the nitrogen, just a minute. How about the nitrogen? The nitrogen is what? sp3. Why sp3? That is correct. Because it's bonded to 3 atoms, then it has a lone pair of electrons. Very good. Okay, so it is also sp3. Okay, yes, go ahead.
You know how, like, because nitrogen has a valence of, but like, you know how usually you have to have 3 bonds, but it only has, oh, it does have 3. Okay, never mind, thank you.
Okay, very good. Okay, yes. How do you want?
Yes, please. Yeah, partial grade period.
Let's move on. Yes. Which one? The oxygen. If it is attached to, okay, what we're saying is each non-bonding pair of electrons. In this case, this oxygen here has this pair of non-bonding electrons. It also has this other pair of non-bonding electrons. Each pair of non-bonding electrons should be considered as a bond. Okay? So therefore, for supposing I give you this molecule here. Supposing I give you this here. What is the hybridization of this oxygen? Yes, what is it? Yeah, go ahead. What is the hybridization of this oxygen? sp2. Okay, why? It has how many non-bonding pair of electrons? 2. Okay, so it has 2 non-bonding pair of electrons. Okay, so each one of them considered as a bond and or an atom, and then it's also bonded to another atom, which is carbon here. So that makes this sp2. Okay, yes. Is it safe to say all double bonds are S? Well, I don't want to make that generalization, but for the most part, yes. Okay. Let us move on. Now, before we go to chapter 2, I do want to revisit the whole idea of hybridization, because I know a lot of you are kind of apprehensive about hybridization. So I want to take a few minutes just to clarify a few other points with regard to hybridization. So I will call this hybridization revisited. Hybridization okay, supposing when we have this molecule here, I will give you 3 molecules. Okay, this is the calculate structure of a molecule called ethane. Now, if I ask you, what type of bond is this do we have in ethane? What kind of bond do we have in ethane? Sigma bonds. Okay, all of these are sigma bonds. These are all sigma bonds, right? Sigma bonds are single bonds, right? In which you have, for sigma bond, you have what we call an edge-to-edge overlap of atomic orbitals in order to form the single bonds. Okay. On the other hand, if I have this molecule here, this molecule we call ethylene. In this molecule we have 4 sigma bonds. This is a sigma bond right here. One of these double bonds here is a sigma bond. This here is also a sigma bond. This here is also a sigma bond, and this is a sigma bond. But this here, the other bond in the double bond, we call a pi bond. This here. Now, supposing I ask you to give me the bonding orbital structure for this molecule called ethylene. If I ask you to give me the bonding orbital structure for this molecule called ethylene, what will you do? Two overlap. Very good. Okay. So Duane is giving us the answer here. So what do? We have 2 carbon atoms. This is a black pen. So we have 2 carbon atoms. Each one of those carbon atoms will have an sp2 hybridized orbital. We have sp2 hybridized orbital. Okay? Because at this point, this carbon here, each one of the carbon wants to bond to 3 other atoms. So therefore, it will mix 2p orbitals and 1 s orbital to form the sp2 hybridized orbital. The other carbon atom will do the same. We have sp2 hybridized orbital, sp2 hybridized orbital, sp2 hybridized orbital. Now, each one of the, according to the valence bond theory, of course, each one of these contains an electron. Now, each one of those carbon atoms now has a p orbital. Keep in mind now the p orbital is perpendicular to the sp2 hybridized orbital. These are the sp2 hybridized orbital. The same thing here. This carbon here has an sp2 hybridized orbital. Okay, so now these 2 carbon atoms, they want to join together. Of course, we know that the hydrogen will be here somewhere. I'll use a different color here. Hydrogen right here. Okay. Now they all want to overlap. So you now have the carbon here, this carbon here, you have this here, this sp2 hybridized orbital overlapping, and then here, 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 and here, and then you have the p orbital perpendicular to those sp2 hybridized orbital. Now we have 2 electrons here being shared by those 2 nuclei. 1 electron here, 1 electron here, 1 electron here, 1 electron here. And of course we now also have hydrogen s orbital overlapping with that, hydrogen s orbital overlapping with that, hydrogen s orbital overlapping with this. That's hydrogen, 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 hydrogen. So if I ask you to give me the bonding atomic orbital for this molecule here, this essentially is what this will look like. Keep in mind also that each p orbital has an electron. So now we have, so far we have shown, in this orbital picture here, we have shown 5 sigma bonds. This is a sigma bond, sigma bond, sigma bond, sigma bond, and sigma bond. The only thing that is now missing is the pi bond. So what happens, it will now be what we call a side-to-side overlap of the p orbital. A side-to-side overlap of the p orbitals. Will give you the pi bond. That is now what we refer to as the pi bond. Now the consequence of this is that because in the pi bond you have a side-to-side overlap, you do not have a direct overlap, those electrons are not as strongly bound to those 2 atoms as in the case of the sigma bond. And there's a consequence to that when we get to chemical reaction. The reason I want to bring this up, when we get to chemical reaction, we are going to begin to see the consequence of the pi bonding. Yes, you have a question? I can't hear you. This here? Let me see. This here? Which one? The connection, the perfect connection between Yes. Oh, this here. This is the single bond right here. This is the sigma bond. That is the head-to-head overlap. So what happens first, you get the sigma bond, which is as a result of overlap of the sp2 hybridized orbital from one carbon and the sp2 hybridized orbital from another carbon. So you get the sigma bond. Then the pi bond is just the overlap of the p orbital, which is perpendicular to the sigma bond. So it's just as if they just overlapping on the side. So it is not an head-to-head overlap. And because of that, you're going to find that molecules that have the pi bond are very reactive, because those electrons are very readily available to undergo chemical reaction. That is why I think it is very important that I stress this. Okay. Okay. So therefore, this will now be your orbital picture. This will now be the orbital picture of this here. That would be the orbital picture of this structure right here, in which each one of these single bond is a sigma bond, and one of the double bond is a sigma bond, and the other is a pi bond. Okay? Everybody follow that. Okay, so that is the case of acetylene. Now, we could also have, supposing we have this molecule. This molecule we call acetylene. By the way, the last one I gave you, that was the example of ethylene. I thought I said acetylene. It should be ethylene. Okay. Now, this molecule here is called acetylene. Now, supposing I ask you to give me the orbital picture of this molecule, what will it look like? Okay, we have a sigma bond. We have another sigma bond here. One of these triple bonds will be a sigma bond, and the two other bonds will be pi bond. So what do you think the orbital picture will look like? Let us try to draw that.
Sorry, are you going to make a star on this?
To do what? Why not? The orbital picture of this here, okay, so we could start with the carbon here, right? Carbon here. Yes, go ahead.
How do you know how many like pi bonds and how many single bonds?
Okay. Keep in mind, when we look at it, if I ask you what is the hybridization of this carbon, you will say what? It's sp, right? So what that is telling me is that you are mixing s orbital and a p orbital to form the sp hybridized orbital. That is what that is telling me. So if that is the case, keep in mind that carbon atom has s, p, p, p orbitals. Okay, so in this case, now you're telling me that you have used s and p to form the hybridization, the hybridized orbitals. Therefore, what that tells me is now you have two p orbitals left. Okay, so therefore, if I tell you to give me the orbital picture, okay, then you have the carbon atom here. Okay, so this carbon here has an sp hybridized orbital, sp hybridized orbital, and this other carbon also has an sp hybridized orbital and sp hybridized orbital. Each one of those will overlap according to what we have here with hydrogen, s orbital. And that's your hydrogen right there. Okay, in which you now have two electrons here, and between these two carbons, you also have two electrons. Now, what is left? You now have these two p orbitals left on each one of those carbons. Okay, so we have to show p orbital. So use another pen to, that's what you say, red pen. P orbital. Okay, the same thing on this carbon here. P orbital. And here you are, another p orbital. So far, what do you have now? How many sigma bonds do you have in this molecule right now? Right now you have 3. A sigma bond between this hydrogen and this carbon, a sigma bond between this carbon and this carbon, and a sigma bond between this carbon and this hydrogen. So at this point, each one of those carbons has how many bonds? How many bonds? No, at this point. No, so far. If you look at this carbon here, based on what I've drawn so far, how many bonds does it have? 2. It's bonded to this. It's also bonded to hydrogen. That's what I've shown you so far. Now, but carbon must have 4 bonds. Its valence is 4. So therefore, what it's going to do, there will be overlap between these p orbitals and overlap between this other p orbital. And that is now how you form your 2 pi bonds. So because in this here, each one of these sideways overlap is a pi bond. Okay? So now you have a pi bond here, another pi bond here, and the one in the middle will be your sigma bond. Okay? Now what does that tell you? When you now look at ethylene and acetylene, which will be more reactive? Acetylene. Because in acetylene you have a lot more electrons that are not under the very strong control of the 2 nuclei. So when it comes to chemical reaction, this actually becomes very important. That is why I want you to understand what is happening here. Yes? Yeah, I know. The book shows that, the book is showing you a cross-section. And I don't want to confuse you by having both of them. Okay. You follow that? Okay. Yes. Okay, so now anyway, so at this point we have completely finished chapter 1. And so now we are going to go to chapter 2. But just to cap this, keep in mind that in the case of the sp2 hybridized carbon, all of the bonds attached to a particular carbon, they are all flat. Okay. Okay, the bond angle will be 120 degrees. Keep that in mind. Now, in the case of the sp hybridized carbon, the bond angle, this bond angle here will be 180 degrees. Let me take this out of here. In the case of the sp hybridized carbon, this bond angle is 180 degrees. So therefore, we say this is a linear geometry. Okay, the same thing here. The bond angle here is 180 degrees. Okay, and also that has some impact on chemical reactivity. Okay, any other question before we move on? Yes. sp3 bond is what? I can hardly hear you. Can you raise up your voice? Yes. Yes. The question is how the bond angle for sp3 carbon is 109.5 degrees. That is correct. And the bond angle for the sp2 carbon is 120, and the bond angle for the sp carbon is 180. Yes. Slightly different? No, that's, don't worry too much about all that. Just as long as you know it within that range, that's all. Yes. sp2 120? Yes. Okay. Okay, so now let us start chapter 2. So officially now we have finished chapter 1. And you're going to find out that chapter 2 is actually an extension of chapter 1. And for the most part, both chapters 1 and 2, they sort of give us some foundational concept for how to explain some of the chemistries that we are going to observe in organic molecules. So it is very important that we understand these two chapters, and you notice that that is one of the reasons I am taking my time to actually slow down and explain both chapters 1 and 2 as we go along, because these are very, very important concepts that you need to understand very well in order to be able to do well in subsequent chapters. Okay. So now, we have in chapter 2, we're going to discuss polar covalent bonds, dipole moments, formal charges, resonance, and acid-base reactions. Now, the question that you want to ask is, what do we mean by polar covalent bonds? You're going to find out this is actually a very simple concept indeed. But before we do that, just like everything else we do, the next slide will simply showing you the outcome objectives for this chapter. In other words, I want you to come back to this slide to see what are those concepts and or topics that we expect you to master during the course of this particular chapter. So I'm going to leave this to you to go through this and read it by yourself. Now, with respect to what do we mean by polar covalent bond, we told you in chapter 1 that we have two types of bonding in organic chemistry. And what are those two types of bonding? Covalent and ionic. Okay. We actually did not tell you this complete story. We're going to find out there's somewhere in between the covalent and the ionic. There's another bond that we call covalent, a polar covalent bond. Because in nature, it is very difficult to actually have an absolute covalent bond. Because covalent bonding means what? What does covalent bond mean? Sharing of electrons. In nature, it's very difficult to have two atoms that are different to share electrons equally. That is very difficult. However, if you have in a case in which, for example, in the case of a hydrogen atom, if you have two hydrogen atoms, one will expect a complete sharing of electrons. So this will be a covalent bond. Okay? That is a sigma bond because you have the s orbital of hydrogen, one hydrogen atom overlapping with the s orbital of another hydrogen atom. That is a case of a covalent bond. That is a perfect covalent bond. That is okay. But if you, on the other hand, if you have atoms, say for example in this case, let's take a look at this molecule here. In this molecule we call chloromethane, we have the carbon-chlorine bond, we have the carbon-hydrogen bond. There is no way to expect each one of these bonding to be a perfect covalent bonding. Okay, so therefore, there is a term that we use in organic chemistry we call a polar bond. In organic chemistry, polar simply means uneven distribution of bonding electrons. So if we say we have a polar covalent bond, that means we have an uneven distribution of bonding electrons. But how will you know that? Very simple. To know that, you simply have to know this table of electronegativity. Okay, nobody expects you to memorize this table. Whenever you need it, this will be made available to you. But electronegativity simply means that each one of these atoms has an affinity for electrons. And a measurement, the relative measurement of the affinity of each atom to attract bonding electron to itself, that is what we refer to as electronegativity. Fortunately, we have a table of electronegativity here. We have the most electronegative atom is fluorine. We give this an arbitrary value of 4.0. We say fluorine has an electronegativity value of 4.0. And what is the electronegativity value for oxygen? 3.5. About nitrogen? 3. About carbon? 2.5. Okay, very good. About chlorine? 3. About hydrogen? Hydrogen? 2.1. Okay. Now, so you could therefore determine whether a bond is polar or not, depending on the different electronegativity of the two atoms that are involved in the bonding. So therefore, if I have take for example, you have this molecule here we call methanol or methyl alcohol. What do we have here? We have carbon is bonded to oxygen, and that carbon is also bonded to 3 other hydrogens. Look at the electronegativity of oxygen is 3.5. Electronegativity of carbon is 2.5. The difference in electronegativity between them is 1.0. Now, anytime the difference in electronegativity between two atoms in a covalent bond, anytime the difference in electronegativity is 5 or above, then you say you have a polar covalent bond. Okay. Either 5 or above. If the difference in electronegativity is 5 or above, just as a rough estimate, 5 or above, then you say you have a polar covalent bond. So if I ask you, I give you a bond, I say, is this a polar covalent bond or not? What do? You go back to the electronegativity table, you look at the electronegativity values for each one of those atoms involved in the bonding, and then you should be able to answer that question based on the difference in electronegativity. Yes, somebody asked a question there. Yeah, go ahead. Yeah, 0.5. Anything? Oh, did I say 5? Oh. Yeah, I'm sorry. I'm glad you corrected me there. Anytime the difference in electronegativity between two atoms is 0.5 or above, then you have a polar covalent bond. Okay. So in this case, the bond between oxygen and carbon here, we will say this is a polar covalent bond. And then to represent that bond, we use a cross arrow. You see this arrow here. Okay, we use a cross arrow to show the direction of polarity. In other words, what we are saying here is that the electron is being pulled towards oxygen. Okay, the electron cloud is being pulled towards oxygen. So that is the direction of polarity. And then we use Greek symbols, sigma here, with a negative sign to show that oxygen has a partial negative charge, whereas the carbon has a partial positive charge, meaning that we are pulling electron away from carbon towards oxygen. Okay? Now, the same thing could be said of right here. The bond between carbon and lithium. In this case, look at the electronegativity value. Carbon is 2.5 and lithium is 1. Okay, so the difference is 1.5. Okay, so what would be the direction of pull of electron? It's towards carbon. In other words, carbon is more electronegative than lithium. So you can now see, we now draw that cross arrow towards the carbon atom, and then we have the negative charge on carbon atom and the partial positive charge on lithium atom. Okay. So these are the way in which we represent bond polarity in organic chemistry. Yes. Say that again. Yes, very good. The hydrogen also. What is the electronegativity between the electronegativity of hydrogen is what? 2.1, and carbon is 2.5. So if you look at this here, between carbon and hydrogen, where would the pull of electron be? Which is more electronegative? Okay, so the pull of electron will be towards the carbon. Okay. No, hydrogen is less electronegative than carbon. So therefore, the electron cloud will be pulled towards the carbon here, but overall, the oxygen will be pulling also electron from carbon to itself. Okay? Yes?
The carbon okay, basically the carbon is pulling it down, but the hydrogen is less electronegative, so it's pulling it up. Does that make a difference?
No. Carbon is pulling electron away from hydrogen. Okay? Okay? But oxygen is also now pulling electron away from carbon. Okay? Okay? So that is the case in which we could determine the bond polarity of a given bond. In other words, a bond between two different atoms, we could determine, okay, what kind of bond polarity do we have by simply looking at the electronegativity. Yes?
You have any dotted line, dash, solid line structures. Are we going to need to know how to draw those two, or is it for the only? Okay.
Yes, but we will get to that. We will get to that later. Okay. Yeah. Yes. The dotted line, they do mean the dotted line means that the bond is going away from you, and the solid is coming to you. But we'll get to that later. Okay. So anyway, right now you could take a look at a given molecule. For example, if I give you this here. Supposing I give you this here, if I give you that here, okay, what would be the direction of polarity between carbon and chlorine atom in this molecule? Be towards the what? Towards the chlorine. So therefore, we are going to represent that by simply drawing this. We use the cross arrow, the arrow meaning that the electron is being pulled towards the chlorine atom, and then we say this has the carbon has a partial positive charge, and the chlorine has a partial negative charge. Now this is very important once again when we get to chemical reaction, because all of these chemical reactions that we are going to be dealing with, most of them will depend on bond polarity. Okay? Okay, so that is why this is a very, very important concept indeed. Now, so far we have discussed polarity of a bond between two atoms. We could also think of polarity of the whole molecule. Okay, bond polarity simply means uneven distribution of electrons. Okay, that bond polarity could also be applied to a given molecule itself, in which you have uneven distribution of electrons within the whole molecule. And we could actually measure that by another concept we refer to as dipole moment. Simply stated, the dipole moment is the measurement of the magnitude of uneven distribution of electrons within a given molecule. There's a slight difference between that and what we just discussed with you in terms of a bond. Because keep in mind, in a given molecule, you have several bonds. The dipole moment, what it does is to measure the magnitude of uneven distribution of electrons within a given molecule. For example, we say in this case, if you look at this here, take a look at the water molecule. Take a look at this water molecule. We say the water molecule has a dipole moment of 1.885 D. The D stands for, that is the unit of measurement of dipole moment. D stands for the bias. Don't need to worry about saying that, just say D. Okay, that is the unit of measurement of dipole moment. And of course, dipole moment is also represented by this Greek symbol mu, which is this here. Okay, so we say water has a dipole moment of 1.85. And then we look at methanol, this other molecule here. We say it has a dipole moment of 1.70 D. And we look at ammonia, we say it has a dipole moment of 1.47 D. What this is telling you is that water is more polar than each one of these other molecules. In other words, there is a greater uneven distribution of electrons within the water molecule than the rest of them. Now, once again, this is important, because when it gets to chemical reactivity, there are certain reactions that will take place in what we call a polar solvent, as opposed to a non-polar solvent. So each one of these solvents here, therefore, we refer to as being polar solvents. Because the net electron distribution within the molecule is uneven. Generally, you're going to have a molecule will have what we call a net dipole moment. If that molecule is asymmetrical, if it is asymmetrical, on the other hand, if a molecule is symmetrical, it will have no dipole moment. For example, supposing we have this. Supposing I have this here. The question that you will be asked, will this molecule have a dipole moment? Nobody is going to ask you what is the dipole moment of this molecule, because you cannot do that. Dipole moment you can only determine by using an instrument. But what we could ask you is, do you expect this molecule to have a dipole moment? Do you? No, because this molecule is symmetrical. There will be no uneven distribution of electrons within this molecule. Okay, so we say, therefore, say this molecule is non-polar. Okay, supposing I give you this here. If I give you this molecule here, do you expect this molecule to have a dipole moment? So the dipole moment will be 0 because it is symmetrical. Now supposing, so the dipole moment for this will be 0. Supposing I have this. Supposing I have that, do you expect this molecule to have a dipole moment? Yes. And what will be the direction of the dipole? Toward the chlorine. So therefore, the direction of the dipole will be here. Yes.
So what does water have a dipole moment for carbon dioxide?
Carbon dioxide? Did you say carbon dioxide?
Yeah.
Oh, okay. You say, okay, this is water here, right? Okay, why does water have a dipole moment? Is that what you're saying? Okay. Keep in mind, this is water molecule. You have non-bonding pair of electron here. Non-bonding pair of electron here. Okay. When we say a molecule has a dipole moment, we're saying there is uneven distribution of electrons within the molecule. So one part of the molecule has more electron than the other part. So that is essentially what we are saying here. So if you look at this, of course, within the individual bond here, okay, we could draw this. Oxygen is pulling bonding electron to itself right here. This also doing that here on this other side. But overall, within this molecule, there is a net dipole moment because there are more electrons on this side of the molecule than on this side of the molecule. Okay, follow that. Okay. Yes. Oh, is it? What time is it? 7:25. Oh, 7. Oh, okay. Sorry. Okay. Folks, when we come back on Tuesday, we are going to continue with chapter 2.